Hey everyone! Alright, in this video we're going to look at these objectives. We're going to examine old regents questions related to what's called electron configuration, something called bright line spectrum, ignore that period there, and electron dot diagrams. Here we go. Question 1. Looks quite wordy, so we're going to read it first, then we're going to underline what might be important information. So, here we go. How do the energy and most probable location of an electron in the third shell of an atom compare to the energy and the most probable location of an electron in the first shell of the same atom? So what's important here? How do the energy and the most probable location of an electron in the third shell of an atom compare to the energy and the most probable location of an electron in the first shell? So it's the third versus the first. Let's look at our choices. Number 1, in the third shell an electron has more energy. Yes, that's true. It's further from the nucleus, it has more energy. And it is closer to the nucleus. No, it's not closer to the nucleus. Number 2, in the third shell an electron has more energy, true, and is further from the nucleus. Hey, write that in there to conserve time. There are a lot of questions. I'm going to stop it there. The answer is 2. The third shell is further from the nucleus. And let me diagram that just a little bit for you before we actually go further. Here's the nucleus. First shell of an electron, of the orbitals that electrons fill. Second shell, third shell. Of course, the third is furthest from the nucleus than the first. Now I'm showing you this illustration prior to the next set of questions because it helps us understand what happens to electrons when energy enters the atom. So what tends to occur is this is called a photon, and what's also good to understand is we could consider this photon a packet of energy. So it has what we call quanta. Quanta means a measurable amount of energy. And what happens when that energy enters this atom? It strikes this electron, and as you can see here on the picture on the right, that electron was in this position and it jumped up to a higher energy level. So that changes our definitions of the atom. See, when the electrons are at their lowest energy state, we call it the ground state. And when they jump up to a higher energy level, it then acquires the name excited state. Now, the most important thing to understand is what happens after that energy is no longer added. Now, let me undo all this writing and give you a different picture. Shrink that one, get it out of the way, and in comes this guy here. Similar picture, but it's showing you that after that excited state atom is here, it's going to drop back down to its ground state and go back to the orbit that it had before. And it is going to now give off that energy that it had absorbed on its way back down to the ground state. Now, later on we'll take a look at the fact that that energy that is given off sometimes can be viewed as visible light. And visible light can be separated into its individual wavelengths of color and give you what's called a spectra, a bright line spectrum. It acts as though it's the fingerprint for that atom. So now on to question 2. A bromine atom in an excited state could have an electron configuration of, well, it's going to be one of these. And to best understand what it could be as an excited atom, we need to look at what that electron configuration would be in the ground state, a non-excited atom. So let's look at the periodic table. And where is bromine? Bromine, where are you? There it is. Bromine. Now bromine in the non-excited state is 2, right here. 2, 8, 18, 7. First energy level has 2 electrons. Second energy level, or shell, 8. Third, 18, and lastly, the valence shell has 7 valence electrons. So what would that look like perhaps as an excited atom? Now remember, 2, 8, 18, 7. Okay, so let's go ahead and write that. 2, 8, 18, 7. Now, if this absorbs energy, one of these electrons here, 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 or even here are going to jump up to a higher energy level and alter the numbers. So, number 1, does number 1 suggest that? It's 2, 8, 18, 6. No, that actually lost an electron. 2, 8, 18, 7. No, that is the ground state. That's the normal condition of the atom. 2, 8, 17, 7. Wait, 2, 8, 17, 7. No, it's missing an electron. Or how about 2, 8, 17, 8? So 2, 8, if this were 17, it means that an electron jumped up to here and became 8. Hey, it's choice number 4. Number 3. Which statement describes how an electron in the ground state becomes excited? Now remember, if it becomes excited, the electrons are going to move out further. And let's see if we can find an answer that matches that. Number 1 says the atom absorbs energy. Good. And one or more electrons move to a higher energy shell. Now I'm just going to tell you right then and there from our previous discussion, that is the answer, but it would be great if you paused, look at 2, 3, and 4 and see why they are incorrect. Alright, number 4. What must occur when an electron in an atom returns from a higher energy state to a lower energy state? Let me bring back this picture. And in this picture it's showing that the atom is in the excited state and the electron that is excited is now returning down to the ground state. What must be happening? A photon, a portion of energy, a measurable piece of energy is being released. Do we have a match here? Look at number 1. A specific amount of energy is released. That's it. Number 5. The bright line spectrum of sodium is produced when energy is. Now, as I said earlier, bright light spectrum is produced when, let's just say, an atom. There we go. Let's just say an atom gets excited. It starts giving off energy as the electrons drop down to their ground state. So in giving off energy, they might be giving off light. Okay? And if that light is allowed to enter a prism, as the light enters, it separates the light into various wavelengths. And those wavelengths will take on a pattern. And that's called the bright line spectrum. A spectrum makes you think of an array of different colors or bands or something. So what would make this happen? And so let's grab my pen. Okay, the bright line spectrum of a sodium is produced when the energy is absorbed as electrons move from higher to lower. Absorb would not make it move from higher to lower. Or when energy is absorbed as electrons move from lower to higher. No, it's absorbing. It's when it gets released. So released as electrons move from higher to lower. Yes, returning back to its ground state. So it is choice number 3. Okay. The isotopes K37 and K42 have the same, Now they're both potassium, they both have the same number of protons, but when we're talking about these bright light spectrums, when we're talking about the electron configurations, we are talking about the electrons. So at this very moment we have to ignore the concept of protons, we even have to ignore the neutrons. And what you need to realize here is that is potassium, and in no way, shape, or form are they saying the potassium is anything but a neutral potassium. So that means that this first potassium here has the same number of protons as that potassium, and because they're neutral, they must also have the same number of electrons, therefore the same electron configuration. So if that atom, or either one of those atoms, gets excited, when those electrons drop down to their ground state, they will give off the same bright line spectrum. Here's number 7. Base your answer to the following question on the information below. The bright line spectrum for 3 elements and the mixture of elements are shown below. So here's an actual picture of 4 bright line spectrums. Lithium, here are the lines that are produced when the light emitted from lithium is separated with a prism. Cadmium, strontium, and a mixture of various lights together. So this question is asking you to identify all the elements in the mixture, which means that in this portion right here, it must consist of all of the lines of lithium if lithium is there, all the lines from cadmium if cadmium is there, and the same for strontium. So let me clean up the picture a little bit and investigate more clearly. Is this line represented in the mixture? Looks good. This line, is it in the mixture? Looks good. This one, yes, and this one, yes. Clean it up. So far we know lithium is there. So lithium is there. Okay, is cadmium there? Well, both those lines are not represented in the mixture. Cadmium is not in the mixture. And strontium, is this line present? Is this line present? This one, yada, yada, yada. Yes, they are. The answer is this mixture is comprised of both lithium and strontium. All right, number 8. Base your answer to the following questions on the electron configuration table shown below. So we have element X, Y, and Z with their electron configurations marked right there. Question: what is the total number of valence electrons in an atom of electron configuration X? So we are investigating this one. And the electron configuration is 2882. The first 2 is the one that is closest to the nucleus. So first shell is 2, second shell 8, third 8, last 2. The answer is 2 because we are trying to focus on this last one. And for that matter, if we want to know what the valence electrons for Y is, the answer would be 3. And for Z, it would be 8. Okay, this is a similar question. Base your answer to question 9 and 10 on the diagram below. We have magnesium 26. What is the total number of valence electrons in an atom of magnesium 26 in the ground state? This is the ground state, so we are looking for that very last shell, and it has 2 electrons. Your answer is 2. All right, question 10 is using the same diagram. Write an appropriate number of electrons in each shell to represent magnesium 26 atom in the excited state. Your answer may include additional shells. So I'm going to give you a variety of answers that could be correct here. We could have 2, 7, 3, suggesting that one of the electrons from the second shell jumped to the third. You could have 1, 8, 3. You could have 2, 7, 2, 1. Anything that suggests that an electron moved to a higher shell would be acceptable. Do not add electrons, do not take any away. Number 11. Magnesium, calcium have similar chemical properties because an atom of each element has the same number of what? Well, right here is magnesium, there is calcium. On close inspection of them, magnesium is 282, calcium is 2882 as far as their electron configurations, and there is your answer. It's because of the valence electrons. And last, which is the electron dot symbol for a chlorine atom in the ground state? Well, here's chlorine. Its electron configuration is 287, and the dot diagram only represents the valence electron. So we are looking for the answer that has only 7 dots surrounding the chlorine. It is not number 1, number 2, number 4. It is number 3. Remember, only the valence electrons are represented in a dot diagram.